Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to provide an example of how to calculate the average power output of a motor. So what we're looking at here, we have this vehicle, and imagine that it's driving up this hill sloped 15 degrees with the horizontal at 10 meters per second. For this example, we're going to assume it has a mass around 1,200 kilograms, and we're going to try to calculate the average power here delivered by the motor. So in order to do that, you have to know how power is calculated and what it is. I define power a couple of different ways, and I've kind of acronymed it here, but power is defined as rate that energy is transferred. That's one way in which power can be defined, or it can be defined as rate that work is done. It doesn't matter which one we use to calculate this. I'm going to go ahead and use this, rate that work is done. And if I'm going to define power like that, then the average power is going to equal total work done divided by total time. Now, as this car moves up the hill, it's moving at constant velocity, so a motion diagram might look something like this. Okay, the velocity vector points this way, and there is no acceleration for this car. So if the car's not accelerating, then the power output of the motor should be constant. And what that means, as far as the problem is concerned, is that the time can be chosen. We should get the same answer if we choose 10 seconds, 2 seconds, 1 second. So I'm going to go ahead and just choose a time frame of 10 seconds. I'm going to call that delta t, 10 seconds. Now, to get the work term, there's a couple ways we could do that. We could draw a free body of the car, and we can get the work term that way by finding the frictional force acting on the car. Basically, that's pushing it up the incline. I'm going to go ahead and get the work term like this. I'm going to write out the work energy theorem. I'm going to call this position 1, this position 2, and write out the theorem of work and energy, which says, the potential energy at position 1 plus the kinetic energy at position 1 plus work done on the car from 1 to 2 is going to equal the potential energy at 2 plus the kinetic energy at 2. And because there's a work term here, I can use the work energy theorem to calculate the net work done on the car. Now, some side thoughts here. The kinetic energy of the car is not changing. So this term right here, the KE1, is going to equal the KE2 in this example, which means they can subtract off. So I'm just going to go ahead and get rid of them. Now, it's not that they're zero. I am not saying that the kinetic energy is zero. What I'm saying is they are the same. So if I subtract this from both sides, they would be gone. All right, potential energy. Anytime you deal with potential energy, you're going to want to define a datum. So I'm going to go ahead and define my datum. And I'm going to put the lowest point in the diagram as my datum right there. And by doing that, so there's my datum, I have now forced PE1 to be 0 because we're at our datum. So the work from 1 to 2 is going to equal the PE2 term. Now, the potential energy, that's going to be an MGH term. We're going to need that height right there for the PE2 term. This distance along here, I'm going to go ahead and draw that in blue as well. This distance along here, we can calculate. The car was moving at 10 meters per second in this example. It did so for 10 seconds. That's going to make this distance 100 meters. From this triangle right here, I'll go ahead and finish that in blue. And keep in mind, this would be a 15-degree angle as well. This height would equal 100 meters times the sine of 15 degrees. So our PE2 term can be written MGH, where the H is equal to this value. So putting in numerical values here, let's see, we got 1,200 kilograms times 9.8 meter per second squared, or Newton per kilogram, whichever unit you prefer, times our height here, 100 meters, times the sine of 15 degrees. That's my shorthand there. And I'm going to go ahead and calculate a value here. Okay, and what I get out of this, I get approximately 30,440 joules. Oh, I'm sorry, I got one more zero here. I got to go back. 304,371. I'm just going to round that to 304,000 joules to three significant figures. All right, so this would be the potential energy of this car here at position 2. So our power, which is equal to our work done, which is equal to 304,000 joules, divided by our time, 10 seconds. So our average power ends up being, let's see, 304,000 joule per second, 30,400 joule per second. Also notice, look at how it's calculated. The 304,000 joules is equal to the work done on the car. It's also equal to the potential energy of the car at position 2. That's why we can use either of these definitions here. Right? Rate that work is done allows us to use this equation basically to calculate it, or power is also equal to rate that energy is transferred. That means that we can calculate it like this: change in energy over change in time. In this case, the car went from a potential energy of 0 plus its kinetic energy to a total energy equal to the kinetic again at 2 plus this potential energy. So this term, this potential energy term, is equal to the change in energy for the car. It's also equal to the work done on the car. That's why we can use either of these equations to calculate the average power. So we got about 30,400 joule per second, or 30,400 joule per second. And just to convert that to a horsepower, remember there's 746 horsepower. Oops, had that backwards. There's 746 watts in 1 horsepower. Keep in mind this is a watt. So we can convert this and we get about 408 horsepower. I'm going to look at that again there. I'm sorry, had that decimal in the wrong place. Approximately 40.75 horsepower. Let's say approximately 41 horsepower. There we go. That sounds much more reasonable. So, all right, this example is designed to demonstrate how to calculate average power delivered by a motor in this case. And again, you can do it either by work divided by time or change in energy divided by time. Doesn't really matter which. You can get the work term via the work energy theorem, or you could calculate the frictional force acting on the car. You know, if I draw a free body of this car at this position, the mg was down, the normal's looking something like this. The frictional force between the tire and the road acting on the car is something like that direction. And you would take this force times this distance to calculate the work done on the car. So, hope this video helps demonstrate these concepts. Have a great day.